User behavior and engagement has always been an important question in social media studies. Here, we pose the question that whether observing in-app activity patterns can help inform users' future engagement. We answered this question by doing analysis on session and graph level information to verify the assumption that in-app activity does indeed help inform future user engagement. If we know that in-app activity patterns can help inform future user engagement, how do we forecast future engagement using such information? We propose to model users' in-app activity patterns as action graphs, and also capturing the temporal element of such action graphs. We then construct an end-to-end, multi-channel temporal GC and LSTM model, and eventually find that our model can effectively predict future user engagement. Here's a brief overview of Snapchat. While user is engaging with the app, he or she can switch from multiple screens to perform multiple actions, such as sending a snap to viewing a story, and we capture the transition probabilities between these actions to form our action graphs. Now, what are action graphs? Action graphs consist of in-app actions we've just seen, and we compute the transitional probability between actions to perform the graph. They are directed graphs with transitional probability as edges and actions as nodes. Here's an example of a densely connected action graph. This is a user who probably uses Snapchat often and is very likely to keep continuing such activity. Here's another example of a more sparsely connected graph. This can be a user that doesn't use Snap often and will likely churn. Let's move on to our models. We utilize graph convolutional network in our model. They are powerful neural networks which train embeddings on graphs with neighbor information. We have our input features, user graphs as an input, fed through a two-layer GC, and then we apply mean pooling to obtain a single graph representation for each graph. This representation is then fed to a linear layer and a classifier for prediction. With the basic GCN component, we further construct a more powerful temporal variation of the model. With our temporal graphs at each time step, we attach a GCN layer structure as previously mentioned. We then encode the output at each time step with a long short-term memory network to capture the temporal information. Finally, we combine multiple information such as macroscopic feature information, activity sequence information, and most importantly, temporal graph information through a classifier to reach the best performance. We found that this model can effectively predict future user engagement. I hope you enjoyed the brief introduction. Thank you, and check out our paper at KDD.